Okay, hello everyone. My name is Lester Allen, and for my crystals project, I got barium cuprates slash strontium cuprate. So pretty much, we'll start with these guys. So cuprates were kind of investigated by Alex Mueller and George Bernatz in the 80s, and they found that ceramic materials became superconductive at higher temperatures than what was previously known. So higher temperatures being 30. They found 30 Kelvin, cuprates became superconductive. And so my crystal structure was this guy, barium strontium cuprate, which has a superconductor above 90 Kelvin. So sorry, or below 90 Kelvin. And so that this is classified as high temperature superconductor. And keep in mind that 90 Kelvin is about negative 97 degrees Fahrenheit, or negative 183 degrees Celsius. So this is high temperature superconductor because metals and other things usually become superconductive at around 1 to 5 Kelvin. So some of its uses include transportation, imaging. For instance, in MRIs, they have superconductive magnets here, and MRIs have a similar structure, and they are very sensitive to magnetic fields, and they're able to image based on that sensitivity. And here's a quick demonstration of how these superconductive magnets can be used for transportation.
So what have we got here? So we have quantum locking. The superconductor is locked in space, and it stays wherever I put it. You see, this is quantum trapping.
That's amazing.
As long as it's
so the
cold,
it's superconducting. It's frozen with liquid nitrogen.
Upside down.
Right.
And it stays locked.
So the fact that it's superconducting is locking the magnetic field in 3 dimensions, right?
Yeah, exactly.
And so now imagine a train with these magnets based on the bottom.
Yeah.
It would move very quickly with less friction.
It's actually floating above the surface.
And be very energy efficient.
Locked above the surface.
So you could tilt it at an angle and it would still fly
around.
around.
Like this, and it will just go around like this. Because I'm doing this.
And it even flies upside down.
Upside down, and then it is.
Okay, so going back to my structure, based on this website, I found a couple of facts about it, and now I used a software called Crystal Maker to construct everything. So let's go in, make a new crystal. I found that this structure was P4 MMM. This parameter, lattice parameter, was 3.93, and along C it was 3.47 angstrom, and angstrom is basically 10 to the negative, 10 to the negative 10. Now we're going to add in our atoms. We have copper at 000. We have oxygen at 1/2 We have another oxygen at 0.001/2. And then we have our strontium and barium. I'm going to do barium first. And it basically constructs our crystal for us. And let's see if this matches. Here we go. And here we go. So, yeah, let me color code this for us. See, it doesn't look like it added our copper. Or maybe I just wrote over it. Okay. There we go. And I believe it matches. Let's put the axes up the way it should be. Okay, looks like we're good to go. Okay, so let me should be a copper. Okay, now we're good. Okay, so let's color code this. I'm gonna make our barium nice red. Our copper can stay a blue. It's nice. And then our oxygen will be a nice orange. Okay. And so from here, we can go in and add the basically atomic radius. So for barium, we get 2.22 angstroms, which is huge. For copper, it's about 1.28, and then for oxygen, it's about 0.6. Okay, so now with the software, we can go in. Here we have our unit cell. We can go in and look at bond angles and look at bond distances. A quick way to do it, we can select all the atoms and actually calculate the distances each atom is from the center atom. So we have it here, which is a little messy to see. So I'll go and do it individually. So bond distance from the copper to the barium is 3.276 angstroms. Then from oxygen to barium is 2.61 angstroms, and then from copper to oxygen is about 1.965 angstroms. So now we can go and do this with our strontium and just compare. You go to File, Edit, our structure. So pretty much strontium would be in the same place, but have a little bit of a different size. Atomic radius should be 2.15 angstroms, so it's a little smaller. And we can go in and do the same thing. Bond distance from strontium to copper, or sorry, that's bond angle. The distance, about 3.276. To the oxygen is about 2.62, the same. And then the distance from these two is 1.965, about the same. So we also know that just looking at our structure, we have a copper, and we have oxygen. Oh, it's the axis is wrong. Flip it over. Okay. We have our copper in the back, we have our oxygen and the strontium, and so pretty much that forms our lattice site. It's the basis of our lattice site. There's 2 oxygens, 1 strontium or barium, and 1 copper. And also looking at this, we can look at the symmetry and then go in and find the space group. So if we're looking at it, the z-axis is pointing at us, is coming out of the board. We have basically a vertical mirror plane. We can slice it here, we can slice it here. We also have another one that's going through here, and then we have our horizontal plane, like looking at the X coming out. We can slice it here. And so looking back with the z-axis, we have 4-fold rotation. We could take this guy to here, or we could take this guy to there, and then take it back around, back. So that's 4-fold. With a simple cubic structure and 3 mirror planes. That sounds like P4MM to me. We got our bond angles. So pretty much now we're left to find the Wyckoff positions. So we kind of plugged them in earlier, but just to talk you guys through it. We have copper here at the 0, 0, 0. We have an oxygen at the 1/2, 0, 0. Another one at the 0, 1/2, 0. And then we have our barium or strontium right in the middle at 1/2, 1/2, 1/2. So this copper would be at 1A for the P4MM. These oxygens would be at the 2F, and the strontium or barium would be at 1D. And based on that, that's the crystal structure that I had. It's pretty interesting. Superconductors are interesting. This is a ceramic. And so if you guys have any questions about the software or about the molecule, let me know. Thank you so much.